right now, if you look at the top multi-view 3D reconstruction models, they are carrying well over 1 billion parameters. But what if, 90% of those parameters are just a massive, inefficient illusion? Today on AI Paper Slap, we are doing a deep dive into a paper called Déjà View, Looping Transformers for Multi-View 3D Reconstruction. And the bottom line for any ML engineer listening today is that the current trend of scaling feed-forward transformers to massive depths for 3D vision is, well, fundamentally flawed.
Yeah, completely flawed.
Sure.
Those billion parameter models are simply using immense depth to implicitly simulate an iterative refinement process, which is wild when you think about it.
Yeah.
Déjà View proves that by explicitly looping a single transformer block k times on per-view V2 features, you can get the exact same result.
Right. You can match or even outperform 1.2 billion parameter state-of-the-art models using only 117 million parameters. And crucially, it exposes that K value as an inference time compute knob.
Exactly. It allows you to dynamically scale performance on the fly without retraining your models. It completely challenges the prevailing bigger is better scaling laws we've been defaulting to in vision tasks.
So today we are going to unpack why explicit iteration is actually a superior inductive bias compared to just, blindly stacking deeper layers. We also need to look closely at the math of what happens in the feature space during this looping.
Right, that phenomenon they call directional refinement, which is fascinating. And of course, for anyone wanting to deploy this, we have to talk about what happens when you push that compute knob too far.
Yeah, because the math literally collapses if you do. But to understand why throwing a single looped block at this works so incredibly well, we first need to look at what traditional multi-view transformers are actually doing under the hood.
We do. If we step back and look at classical 3D vision, before transformers basically took over everything, recovering a 3D structure from 2D images was handled by a structure from motion pipeline, or SFM.
And that definitely wasn't a single feed-forward pass, right?
Not at all. I mean, a classic SFM pipeline is a highly structured multi-step optimization problem. You first have to extract features from your different 2D images and match them across the views.
Okay, and then from those matches, you move into pose estimation to calculate exactly where the cameras are positioned in 3D space.
Exactly, yeah. Once you have a rough idea of the cameras, you use triangulation to plot the 3D points of the object or the scene, but you aren't done there. You then enter global bundle adjustment.
Right, bundle adjustment. That's where the real heavy lifting happens. You are jointly optimizing both the 3D point positions and the camera parameters, right, just to minimize reprojection error.
You are. And what is critical to understand about minimizing that reprojection error is that it is inherently, unavoidably iterative. The camera poses depend on the 3D points, and the 3D points depend on the camera poses.
Oh, right, so you just cannot solve it in one shot.
No, you can't. The algorithm naturally alternates between registering new views, evaluating the error, and readjusting its previous geometric estimates. It is literally a loop by definition.
But the modern deep learning approach basically looked at that elegant mathematical loop and decided to just brute force it with capacity. The recent wave of multi-view transformers try to approximate that iterative loop implicitly.
They do, yeah. Models like VGGT or DA3G.
Right. It's like if traditional SFM is a single master sculptor slowly carving out a shape, stepping back, looking at it, and refining the chisel work over and over.
I like that analogy.
Thanks. But what the feed-forward transformers are doing is building a giant assembly line. You have 50 different robots, and each one just makes one tiny chip on the marble as it passes by.
Right. To get the same result, you need way more space, way more power, and an enormous amount of redundant layer-specific parameters. The assembly line analogy highlights exactly why this is so parameter inefficient.
Because you are assigning unique weights for every step.
Exactly. You are allocating entirely unique sets of weights, independent query, key value projections, independent MLP layers for every single step of a process that is fundamentally just repeating a geometric refinement.
And researchers have actually looked into this, right? Like looking at the representations across the decoder depth of these massive models.
Yeah, recent analytical studies prove this out. They are just progressively refining the same predictions. Furthermore, if you analyze the weight matrices of contiguous transformer layers in these deep networks, the cosine similarity is often incredibly high.
Wait, really? So layer 39 and layer 40 are basically identical?
Basically, yeah. They're essentially learning to apply the exact same mathematical operations.
So if layer 39 and layer 40 are doing the exact same math, it begs the question, why are we storing two sets of weights at all? Why not just route the data back through layer 39?
Which is exactly what Déjà View does. It completely strips away the assembly line.
Okay, let's break down how they actually build this. The architecture starts by extracting per view features, and they specifically use Dyno V2 for this, right? The VITB model equipped with 4 register tokens.
Yes, the register tokens are a very specific and crucial architectural choice here.
I want to pause on those register tokens, actually, because why are those necessary for this feature extractor?
Well, it's a critical detail for dense prediction tasks, like 3D reconstruction. Standard vision transformers have this known flaw. They tend to produce feature artifacts.
Feature artifacts, like glitchy patches in the image.
Yeah, exactly. Because the attention mechanism needs to store global image information, things like lighting, overall context, or scene type. And it often just dumps that global information into arbitrary background patches that lack useful local features.
Oh, wow. So you end up with these massive outlier tokens in the middle of a blank wall just because the model needed a place to park some global context.
Precisely. If you are just doing image classification, you don't really care. The CLS token pools it all anyway. But if you're doing multi-view 3D reconstruction, every single spatial patch matters.
Right, because if a patch on a wall is corrupted because it's secretly holding global lighting data, your geometry in that area will just be completely warped.
Exactly. So register tokens solve this. They are simply empty, learnable tokens appended to the sequence. They act as a dedicated sink for that global information.
That makes a lot of sense. So the model learns to route the global context into the register tokens, leaving the actual spatial patch tokens perfectly clean and artifact-free.
Which is exactly what Déjà View needs before it starts the geometric refinement.
Okay, so we have these clean Dyno V2 features. Then, instead of passing them through a deep stack of unique decoder layers, Déjà View routes them into a single transformer block.
Right. And it just loops that exact same block with the exact same weights recurrently for K refinement steps.
And the genius here is in the training protocol, right? They don't just pick a static number for K.
No, they don't. During training, the number of refinement steps is randomly sampled from a uniform distribution between a minimum value, K-min, and a maximum value, K-max.
From an engineering deployment perspective, this is the killer feature. By randomly interrupting the refinement process during training, you are forcing the network to be useful at any point in the loop.
Exactly. It has to give a valid 3D output no matter when you stop it. It essentially turns K into an inference time compute knob.
I love that. I can literally just slide a bar to trade compute for quality depending on my hardware limits without ever loading a different checkpoint.
Yeah, if you are deploying on an edge device in a robot and need ultra-low latency, you just set K to 2 or 3. If you are running offline processing on a server farm and want maximum accuracy, you crank K up to 10 or 15.
And let's look at the actual efficiency gains here because they are massive. Déjà View achieves all of this with just 117 million parameters.
Right, which is tiny compared to the alternatives.
Yeah. Yet, across a really diverse suite of benchmarks like ScanNet++ for dense indoor scenes, 7 scenes, and ETH3D for outdoor environments, it matches or beats the current heavyweights.
It's super impressive. It outperforms MAST3R, which has 689 million parameters. It beats Pi3 at 959 million.
And it goes toe-to-toe with DA3G and VGGT, both of which are over 1.2 billion parameters. So we're talking about a 10x reduction in memory footprint. That completely changes how you provision GPUs for this kind of workload.
It really does. It's a game changer.
But I have to push back here for a second. As an ML engineer, my instinct is that this shouldn't work this well.
Oh. Why is that?
Because we are taught that giving a neural network more unique parameters makes it more expressive. You give it the capacity to memorize highly complex manifolds and learn nuanced, stage-specific transformations.
Right. The traditional scaling argument.
Exactly. If I have 16 unrolled layers, layer 1 can specialize in gross geometric alignment, and layer 16 can specialize in hyperfine subpixel refinement.
Yeah.
Shouldn't an unrolled network have strictly more expressive power than a network forced to use the same weights over and over?
It's a really great question, and it highlights a very common misconception in deep learning. You are entirely correct that the unrolled network has more capacity.
Or it has a larger parameter space.
But capacity does not automatically equal generalization. To address exactly this skepticism, the researchers ran a rigorous ablation study.
Oh, they actually tested it.
They did. They built a fully decoupled variant of Déjà View. They took the 16 recurrent steps and unrolled them into 16 independent transformer layers with 0 weight sharing.
Okay, so keeping the training data and compute budget exactly matched.
Exactly the same. And the result, the looped version consistently outperformed the unrolled version.
Wow, really? The looped version won?
Yeah, and the reason comes down to inductive bias. When you unroll the network and give every layer its own parameters, you are giving the network enough rope to hang itself.
How so? Like overfitting.
Precisely. The early layers overfit to the early stages of reconstruction, learning brittle heuristics for gross alignment. The late layers overfit to the final polishing stages.
But 3D reconstruction is an inherently cyclical problem. The rules of projective geometry do not change whether you are on step 2 or step 15.
Exactly. By forcing the weights to be shared across every single step, you act as a powerful regularizer. You completely prevent that stage-specific overfitting.
So the model is forced to learn a single, universally robust update rule for geometry refinement. It has to learn a core algorithm that is fundamentally sound no matter where it is applied.
That's it exactly.
Okay, that actually makes perfect sense. If you give the model the capacity to cheat and memorize specific stages, it will. By constraining it, you force it to actually learn the underlying physics.
Right. It learns the geometry, not the shortcuts.
But wait, if it's the exact same weights being applied every single time, how does the model know if it's doing that gross alignment versus the fine polishing? Does it just have no concept of time?
Well, it does, and that's the one small exception to the strict weight sharing. To help the single block apply this universal rule effectively at different stages, they introduce time-conditioned residual gates.
Okay. Time-conditioned residual gates. How do those work mathematically?
It's quite elegant, really. Instead of the block just computing an output based on the input features, they introduce a time embedding.
Like a sinusoidal positional encoding?
Exactly. One that represents the current step integer, k. They pass this time embedding through a small, lightweight, multi-layer perceptron to generate scaling and shifting parameters.
Okay, and then those parameters dynamically modulate the outputs of the attention and MLP branches inside the transformer block.
Yes, and crucially, these residual gates are zero initialized. This means at the start of training, the gates do absolutely nothing. The block acts as a pure, unconditioned recurrent loop.
But as training progresses, the model learns to slightly scale and shift the activations based on the current step.
Right. It gives the block a lightweight sense of time to adjust its universally learned rule, without requiring entirely separate geometric weights for every step.
So the heavy lifting, the core geometric reasoning, is entirely shared. But the time-conditioned gates act like a subtle clock on the wall, letting the network know how far along in the refinement it is.
That is a perfect way to put it, yeah.
Well, that leads me to a huge question about the feature space itself. If we are passing the feature representations through this exact same geometric update rule over and over, what is mathematically happening inside the residual stream?
That's where things get really interesting.
Because my assumption with any recurrent system, like a deep equilibrium model, is that it's trying to find the fixed point. It's trying to refine the features until they settle into a perfect, unchanging state.
That is exactly what the authors expected to find as well. But the per-iteration analysis of the residual stream revealed something entirely different.
Oh, really? It doesn't settle down?
No, the recurrence does not contract to a fixed point in the high-dimensional feature space. In fact, after a very short initial contraction, the first couple of steps, the norm of the state vector starts growing monotonically.
Wait, the actual magnitude of the feature representations, the numbers just keep getting larger and larger with every single loop?
Yes, they grow monotonically.
But wait, the final 3D geometry it outputs gets better and sharper with every step. How can the internal representation be growing without bounds if the final output is stabilizing?
This is where we get to the concept of directional refinement. While the absolute magnitude of the state vector is growing, the direction of that vector in the high-dimensional space is stabilizing.
The direction stabilizes, but the size grows.
Right. The researchers measured the cosine similarity between the state at step k and the final state at kmax. As the iterations progress, that cosine similarity rapidly approaches 1.
Okay, so the angle is locking in.
Exactly. And at the same time, if you look at the relative norm of the update, meaning the size the change the block makes relative to the massive size of the current state, that ratio decays significantly.
Ah, I see. It's like a rocket ship firing its thrusters in deep space. It's accelerating constantly in a very specific direction.
I love that. A rocket ship.
Yeah, like the speed, or in this case, the state norm, keeps increasing monotonically. The numbers are getting huge. But the heading, the actual vector direction it's pointing, is completely locked in and stable.
That is exactly the dynamic. But your confusion earlier is warranted, because from an ML engineering perspective, Feeding a continuously growing feature vector into a standard linear output head is a recipe for disaster.
Oh, absolutely. If your vector magnitudes keep growing, your final coordinate predictions will blow up. The geometry will explode.
Right. The crucial architectural mechanism that saves this whole process is the layer norm sitting right at the input of the decoder.
Let's break down the math of that layer norm, because it must be doing a lot of heavy lifting here to save the rocket ship from exploding.
It is. Think about the standard layer norm equation. For a given feature vector, you subtract the mean of the features, and then you divide by the square root of the variance.
Right, basic normalization.
But when the magnitude of the entire vector scales up, when the rocket accelerates the variance across that vector, also scales up proportionally.
Oh, I see. So because you are dividing by a correspondingly larger variance, the layer norm effectively strips away the raw magnitude of the vector.
Exactly. It completely normalizes the magnitude out of the equation, preserving only the relative activations between the different channels. It only preserves the direction.
That's brilliant. Because of that layer norm step, the internal state can grow as large as it wants. The decoder only ever sees the normalized direction, which is converging.
Exactly. This allows the decoded representation to stay perfectly stable and produce progressively sharper 3D points, even as the internal state norm flies off into infinity.
That is such a clever interplay between the recurrent dynamics and the normalization layers. But this accelerating rocket ship analogy raises a massive red flag for anyone who wants to push the limits of that compute knob.
Yeah, the extrapolation issue.
Right. We know the model was trained with a random k up to a specific kmax. Let's say kmax was 16. What happens if I deploy this model and I decide I have unlimited compute budget for one specific scene?
Like turn the knob all the way up.
Yeah, I want hyper-resolved geometry, so I set K to 100 on a Friday night and let my GPU cook. If the heading is locked in and layer norm is stripping away the magnitude, shouldn't it just keep making infinitely perfect refinements?
It's a very tempting idea, but the researchers explicitly tested this extrapolation, and it results in a catastrophic failure mode.
Wait, really? It fails?
Yeah. If you iterate beyond the maximum steps seen during training, the model completely collapses. The output 3D geometry essentially turns to noise.
But why? If the layer norm is dividing out the massive variance, why does the geometry turn to noise?
Because of how the variance is growing. Remember that the state norm is naturally drifting upwards with every step. Up to Kmax, the network is seeing these magnitudes.
So it knows how to handle them.
Right. It knows how to keep the distribution of values across the channels relatively balanced. But when you force the model to extrapolate past Kmax, you are pushing the network into a completely unseen regime of magnitude drift.
Oh, so the growth isn't uniform anymore.
Exactly. What the researchers found is that when you do this, the growth doesn't stay balanced. A handful of specific feature channels start to grow entirely out of proportion to the rest.
They become massive, extreme outliers.
Yes. And when you have massive extreme outliers in a vector, they completely dominate the variance calculation in the layer norm denominator.
Right. The variance explodes because of those few rogue channels.
Exactly. So when the layer norm divides the entire vector by that massive variance, it squashes the signal in all the other useful channels down to near zero.
Oh, wow. So the relative information, the precise direction that the rocket ship was pointing is totally destroyed.
Yep. The decoder receives essentially a flatlined vector dominated by noise, and the 3D reconstruction instantly collapses.
So the inference knob is incredibly powerful, but it is strictly bounded by your training distribution. You cannot extrapolate recurrent depth for free.
No, you definitely cannot. It's a hard limit.
That is a phenomenal warning label for anyone implementing this. You can dial it up dynamically, but do not dial it past what it practiced in training, or the layer norm math will just eat your signal.
It's a vital takeaway for sure.
Well, let's summarize exactly what Déjà View has brought to the table. We have seen proof that for inherently cyclical, iterative problems like multi-view 3D reconstruction, where you are constantly reevaluating pose and geometry relying on massive feed-forward depth, is a trap.
It really is. It is incredibly parameter inefficient to just stack layers.
Right. By taking the exact same transformer block and explicitly looping it, you cut parameter counts by 90%. You introduce a highly flexible inference compute knob that lets you balance latency and quality on the fly.
And most importantly, you force the model into a fundamentally stronger inductive bias.
Yeah.
You strip away its ability to overfit to specific stages and compel it to learn a true, directionally refining algorithm for geometric updates.
It is a brilliant piece of ML architecture. But, looking at Déjà View leaves me with a much broader question for the entire field of AI right now.
Oh, What's that?
Well, we just spent this time proving how explicit looping is a vastly superior inductive bias for the step-by-step nature of 3D reconstruction. But look at the wider landscape. Right now, companies are spending hundreds of millions of dollars training trillion-parameter deep feed-forward models for other tasks that are also inherently iterative.
Like LLMs.
Exactly. Think about agentic reasoning in LLMs, where the model has to plan step by step. Or complex code generation, where you write a function, check the syntax, and revise. Or even physics simulations.
That's a really interesting point. Those are all cyclical tasks.
Right. So if Déjà View is right about the wastefulness of simulating iteration with depth, are we currently wasting billions of parameters in those fields too? Are we building giant assembly lines of redundant layers for reasoning and coding when what we really need is just one really good, explicitly looped robot?
It's a profound question. The parameter bloat might be totally unnecessary.
It is definitely something to think about the next time you see a model's parameter count jump by another 100 billion. Thanks for joining us for this deep dive, and we will see you next time on AI Paper Slop.